Fractals have been around since 1976, and in just the span of 40 years, dozens of developments have been made. But how are such formulas created? What techniques do programmers use to zoom to thousands of digits, and how can you try it out? Welcome to the Fractal Tinkerer. Hope you stay around. This guy is Benoit Mandelbrot. Known as the father of fractals, he was a remarkable mathematician and someone who worked at IBM. At IBM, he tackled a problem related to noise on telephone lines, which would cause increasing amounts of distortion, and Mandelbrot introduced the term fractal in 1975 to describe these patterns. The concept of the Mandelbrot set is simple yet complex. Literally, this top formula is used for every iteration for the most famous fractal, the Mandelbrot set. This fractal involves a real and imaginary part of a number, which you can imagine kind of like a point. The formula at the bottom is applied many times, which changes where the point is located. However, the original point's coordinates are added to the new point.
What we do is iterate this formula a bunch of times, test if the point is out of the boundary each time, and if it is, we stop iterating. We can then add a palette of colours based on how long it takes to exit. If it never escapes, the pixel is coloured black instead.
You'll notice, however, that the fractal doesn't seem to be smooth. But why? In order to fix this, we need to do two things. First, increase the maximum boundary of the Mandelbrot set to a value like 1000, and second, use logarithms to approximate this. That way, the fractal looks much smoother and higher quality. The next thing you may be wondering is, how do we render fractals so deeply? Well, this is where perturbation comes in to save the day.
On a more serious note, I am certainly not a licensed mathematician, so if you can understand what this is saying, please comment below and I'll pin it. Anyway, perturbation involves a high-precision reference orbit, which means that you're storing a high-precision number. Essentially, computers normally use floating point values. In this case, doubles are used for calculation, which means it can store slightly below 16 decimal places worth of number data. However, when zooming to thousands of digits, custom algorithms can be used. The Carat-Suba algorithm, for example, can speed this up, but if you can understand this diagram, I'm sure you know what it means. Since I don't. But anyway, let's get back to how perturbation merges high precision and low precision values. The idea is this. One single iteration of high precision is calculated, which becomes the reference orbit. This can then compute many points around in terms of small offsets. But why? Well, you see, although there are only 53 bits of precision in floating point, the exponent can range from 10 to the power of 300 to 10 to the power of negative 300, which is certainly a wide range. Normally, you don't need more than that 16 digits of precision with this small value, which is called epsilon, or the funny E symbol. However, sometimes coordinates can diverge, which means that you need more than 16 digits of precision. In that case, you'll have to create another reference orbit. However, glitches with this can occur. We have to rely on a custom method to fix this, and with a bunch of new ideas. People in fractal communities eventually discovered a method to get around this. Using the formula above, they can detect floating point errors by testing the inequality below. By the way, if this doesn't make a lot of sense, don't worry about it too much. Fractals are very complex, and the concepts of perturbation theory are too. Here's an example of a fractal glitch in Calais Fractala 2, which was an old fractal generator. Although it isn't quite as new and shiny as the modern ones, this one pioneered the eventual rise of Calais Fractala 2 Plus. Here's an example of me zooming deep into a fractal and trying to discover a new pattern. I'll go through the process and what makes fractals look so stunning. Try to catch some patterns along the way. Did you see how amazing that was? In particular, you might be wondering how fractals decide, they're not really deciding, on how they look. Well, the start of where you zoom determines that. Here are a few examples. Did you catch what's going on? Notice how the places where we can zoom into a mini-brot, that's where you can find a copy of the Mandelbrot set inside of itself, seem to change based on where we started zooming into. This is another reason why fractals are so stunning. They can sort of remember where they were zoomed into and preserve those patterns. However, there is more to iteration, optimization, and calculation than meets the eye. In the case of a callus fractala 2, a combination of fixed point and floating point is used. Floating point representation uses variable digits for the mantissa and exponent, allowing for a wide range of values but with variable precision. On the other hand, fixed point representation uses a consistent number of digits before and after the decimal point, providing predictable precision but with a more limited range. Custom algorithms can be used for floating point that allow exponents in the hundreds of millions of digits. At that point, computer memory becomes the limiting factor. In addition, bilinear approximation is a thing that can speed things up. Unfortunately, I don't understand this quite well either. So again, if you know how this works, please explain it to us. Interior detection is also a thing, but we won't get into that either. If you like similar content, please like this video. And if you're really feeling like it, please subscribe. See you next time in the Fractal Tinkerer in part 2 of Fractals, where we dive into Newton-Raphson zooming, other types of fractals including 3D ones, and more.